Hello and welcome to Analytical Instrumentation with Bhumika Sharma. Today's topic of discussion is Basics of UV Visible Spectroscopy, which includes Introduction to UV Visible Spectroscopy, Beer-Lambert-Bouguer Law, Classification of electrons in a molecule, electronic transitions and their properties, selection of solvent for sample preparation, broadness of peaks in UV visible spectrum, spectral shifts, factors leading to spectral shifts, and deviation from Beer-Lambert-Bouguer law. So the UV region is basically from 190 to 350 nanometer, and the visible region is from 350 to 800 nanometer. But we generally consider it as UV region from 200 to 400 and visible region from 400 to 800. I have already told you about electronic transitions in my previous video. As you can see, the molecule absorbs energy and is the molecular orbital is divided into two: highest occupied molecular orbital and lowest unoccupied molecular orbital. When the molecule gain energy, the electron from the highest occupying molecular orbital of the ground state transfers to the lowest unoccupied molecular orbital of the excited state. That is from HOMO to LUMO transition. And the energy gap delta E will be equal to E2 minus E1. That is energy from the excited state to energy from the ground state. The wavelength regions, their absorbed color and the transmitted color of visible region are discussed in this table. As you all know about why we see different colors, the complementary color is seen to our eyes, why the sky is blue, and also why the traffic lights are red. These all questions depends on just these wavelength regions. Now, Beer-Lambert-Bouguer law. Bouguer and Lambert stated that the absorption was directly proportional to the path length or depth or thickness of the sample if we keep the concentration constant. Beer determined that if the sample thickness was constant, then absorption is directly proportional to the concentration. In combination, we can say that according to the Beer-Lambert-Bouguer law, which is also known as Beer-Lambert law or Lambert-Beer's law, the absorption is directly proportional to the path length as well as the concentration of the absorbing species, where A is equals to ABC, where capital A is the absorbance, small a is the absorptivity, B is the path length, and C is the concentration of the absorbing substance. You must have seen in different books that in some books it is written, the Beer-Lambert law is written as A is equals to ABC, and in other books it is written as A is equals to epsilon BC. Is there any difference between A and epsilon? Yes. A is the absorptivity with the unit of centimeter per gram, whereas epsilon is the molar absorptivity with unit centimeter per mole. The optical path length is the same. We can also consider L in place of B. It is given in centimeter, but the unit of concentration varies. In absorptivity, the concentration will be gram per liter, whereas in molar absorptivity, the concentration will be moles per liter, where epsilon is the molar absorptivity constant or molar extension coefficient. It is a measure of how strongly light is absorbed, and depends on the wavelength and the nature of the absorbing material. It basically tells us about the intensity of absorption. Key points to be considered are the incident radiation should be monochromatic, highly collimated beam with no internal reflections is favored. Highly collimated beam means parallel. Parallel path should be given to the incident radiation so that all rays of the incident radiation travel equidistant parallel path through the absorbing sample. The the path of the radiation should be same for all the absorbing species of the sample. Avoid non-linear optics such as high-power laser light source to avoid alteration in the ground state population of the absorbing species. Next is the absorbing sample must be homogeneous and it do not scatter or reflect the incident radiation. No suspended particles should be there in the sample. The absorbing species must behave as independent moieties. I'll tell you this later. Classification of electrons in a molecule. There are basically three different types of electrons, that are sigma electrons, n electrons and pi electrons. Sigma electrons are covalent single bond electrons that possess too high excitation energy. Paired non-bonding outer shell electrons are also known as n electrons, such as lone pair present on N, O, S and halogens. They possess very low excitation energy. Electrons in pi orbitals uh, are the double or triple bond electrons that are most readily excited and are responsible for the majority of visible and UV light absorption. The electronic transitions that take place are, these are the bonding electrons, sigma and pi. These are the anti-bonding electrons and n is the non-bonding electron. The electronic transitions are n to pi star, pi to pi star, n to sigma star, pi to sigma star and sigma to pi star and sigma to sigma star. As you can see there, in these three electronic transition, the energy gap is very large. Thus, the wavelength is very low and it does not lie in the UV visible region. It is less than 180. Thus, we'll only consider these three transitions. Now, electronic transitions and their properties. Transition N to sigma star and N to pi star. These are also known as the forbidden transitions. Why? Because N to sigma star exhibit wavelength in the region less than 220 nanometer. So it falls under the vacuum UV region basically. Its molar absorptivity is 10 to the power 2 to 10 to the power 4. Intensity will be low to medium. Bands are single. Examples of N to sigma star transitions are amines, alcohols, ethers, thiols, but they should not be included in the conjugation system. An exception is the transition of cyano groups is N to pi star, but it lies in this region. Now we'll talk about N to pi star transition. This transition is also known as forbidden because the intensity is very low. As you can see here, the energy absorbed is very low. Thus, the intensity is very low in these type of transition. That is why they are forbidden. The energy is low, thus the wavelength is high. As I have already discussed about the relation of energy and wavelength, they are inversely proportional in my previous video. The link is given in the description box. 250 to 360 nanometer, its molar absorptivity is 10 to 10 to the power 2. Intensity is low. number band single, and the molecules possessing N2 pi star transition are carbonyl, nitrogen dioxide, etc. Now we'll move on to the pi to pi star transition. This is the most favored transition. It lies in the region above 200 nanometer of wavelength. Its molar absorptivity is 10 to the power 3 to 10 to the power 4. Intensity is medium. Number of bands are 2. Examples of molecules possessing this transition are aromatic compounds or polycyclic unsaturated hydrocarbons. Exception is in polynuclear aromatic compound with more than one aromatic ring, 3 bands may appear. And there are certain molecules which possess both N2 pi star transition as well as pi to pi star transition. These molecules are ketones, acids, esters, amides, acids, carboxylic acids. The wavelength region, 2 bands were seen in it. Intensity of one band, that is of N2 pi star, is very low, whereas the intensity of pi to pi star is high. Its molar absorptivity is more than 10 to the power 3. Its wavelength lies in the region, and for N2 pi star band, it lies in the region of more than 300 nanometer, whereas for pi to pi star, it lies in the region of less than 250 nanometer. Selection of solvent for sample preparation. What we have to keep in mind while choosing a solvent for sample preparation. Firstly, it should not absorb radiation in the same region as that of the analyte so as to avoid the overlapping. That is the reason why non-conjugated solvents or saturated solvents are preferred. Second is analyte should be completely dissolved in the solvent. No suspended particle should be there to avoid the reflection or scattering phenomena. And the third one is depending on the transition within the analyte of interest, polar or non-polar solvents are selected. That I'll discuss later. Solvent for UV. This is the table showing the cutoff point or lambda max for the solvents. You must not memorize all these values, but you have to keep in mind that the solvent should not possess pi to pi star or n to pi star transition, or avoid the solvent that shows the transition in the same region as that of the analyte. UV visible spectrum, it is a plot between absorbance and the wavelength. Why the peaks are broad in UV visible spectrum? As I have already discussed about the transition in spectroscopy in my previous video, there are basically 3 types of transitions: electronic transitions, vibrational transitions, and rotational transitions. If I'll apply a certain amount of energy that is sufficient enough to transfer atom or molecule from the ground electron energy level to the excited electron energy level, thus it would also lead to the rotation and vibration of the molecule, as you can see here. Thus the UV visible spectrum possesses all the 3 transitions that are electronic, vibrational, and rotational, and shows broad peak. If we talk about FTIR spectrum, the possible transitions are vibrational and rotational. And if we talk about NMR, the only transition occurring is rotational. Thus, the peaks become narrower. I'll talk about NMR and FTIR in my future videos. Spectral shifts. There are basically 4 types of spectral shifts depending upon the molar absorptivity constant value and the wavelength. Bathochromic shift. In bathochromic shift, there is a shift towards the longer wavelength region, that is the red shift. In hypsochromic shift, there is a movement towards the shorter wavelength region, that is towards it is also known as the blue shift, as we all know, Vib-Gyor, UV visible region. uh, up in hyperchromic shift, the epsilon max value will get increased, or we can say the intensity will get increased. In hypochromic shift, the intensity will get decreased. Factors leading to spectral shifts. Temperature. Low temperature is suitable for UV visible spectroscopy as absorption is higher at low temperature. Other factors include conjugation, solvent, pH, chromophores, and auxochromes. I'll discuss each one of them separately. Electron releasing groups. They increase both the wavelength and the intensity. Thus, they led to the bathochromic and hyperchromic shift. Electron withdrawing group acts as chromophore and do not show any spectral changes, like uh, acting as chromophore, it would lead to a very little bathochromic shift. Effect of conjugation. Conjugation is the alternate double or triple bond. That is where multiple bonds are separated by just one single bond each. They are said to be conjugated. As in case of pi to pi star transition. The greater the degree of conjugation, the greater is the shift towards the um, red region or the bathochromic, longer wavelength region. Conjugation of double or triple bonds with non-bonding electrons also result in spectral changes and is known as hyperconjugation, as you can see in the N to pi star transition. This type, the conjugation in the N to pi star transition is known as hyperconjugation. Conjugation would lead to increase in the wavelength. So it will move towards the longer wavelength region or will lead to the bathochromic or the red shift. Solvent effect is also known as solvatochromism. Uh, as you can see here, both the transition pi to pi star and n to pi star are given in this picture. If we use polar solvent, say for example water, right? So oxygen will have lone pairs or non-bonding electrons. If we talk about pi to pi star transition, electrons will tend to move towards the more stable state, right? So the polar molecule will be attracted towards the excited electrons more to get stabilized. So the energy gap would decrease when we use polar solvent in pi to pi star transition. And if the energy gap would decrease, the wavelength could get increased. Whereas in case of n to pi star transition, as n orbitals are more stabilized than the pi star orbitals, the energy gap would increase. Why? The lone pair of oxygen would interact with the non-bonding electrons and it gets stabilized. So more activation energy is needed to transfer the ground state electron towards the excited state. So, depending on the transitions within the analyte of interest, polar or non-polar solvents are selected. Sometimes polar solvents form solute solvent complex due to hydrogen bonding that could interfere with the results. In N to pi star transitions, polar solvent make hydrogen bonding with the ground state and result in increase in the energy gap between the ground and excited level state levels. Hence, it shifts the spectrum towards the shorter wavelength. or hypsochromic shift. In contrast to this, in case of pi to pi star transitions, polar solvent form hydrogen bonding with the excited state that leads to decrease in the energy gap and shifting the spectrum towards longer wavelength. That is, towards bathochromic shift is there. Effect of pH. The anion form absorbs at a higher wavelength and with a greater epsilon. That is, if we talk about alkali, it will release anions, OH negative. Anions would lead to shift towards the longer wavelength region and towards the higher intensity region. Thus, they led to the bathochromic as well as hyperchromic shift. Effect of chromophores and auxochromes. Chromophores are the absorbing groups of a molecules that are covalently bonded with a compound. Examples of chromophores are nitro, ethylene, etc. A molecule containing a chromophore is called a chromogen. Basically, a chromophore is a unsaturated moiety. If we talk about ethylene, it has double bond. If we talk about nitro, it possesses both it possesses N to pi star transition. If we talk about ethylene, it possesses pi to pi star transition. So if we increase the conjugation, we'll let the wavelength would also get increased and it will move towards the bathochromic shift or red shift. An auxochrome does not itself absorb radiation, but it enhances the absorption by a chromophore. Examples are hydroxyl groups, amino groups, and halogens. All these groups possess lone pairs that, when attached to the unsaturated compound, possess N2 pi star transition. Independently, an auxochrome does not influence spectral shifts. These are some examples of chromophores and their lambda max. Chromophores are added to increase the wavelength of the compound and to move the compounds towards the bathochromic shift. Deviations from Beer-Lambert-Bouguer law. There are basically two types of deviations, that are chemical deviations and instrumental deviations. Chemical deviations can be because of molecular interaction, that is dissociation or formation of a new molecule due to hydrogen bonding, or it can be due to high concentration. Basically, at high concentration, the individual particles of analyte do not behave independently. Thus, the resulting interaction between particles may change the value of molar absorptivity constant. Instrumental deviations include stray light, that is light reaching the detector without passing through the sample. It can be because of if you like open the compartment between the process, when the process is going on, the light of the room will enter to the detector without will enter to the detector. This will lead to stray light effect, right? So it is avoided. The compartment is is made up of complete black color, so that to avoid absorption of any other kind of radiations. Polychromatic radiation source is not used, as I have already discussed that polychromatic radiation source would lead to complex spectrum, because if there is a compound present in the sample that could interact with other other regions of the radiation source, then we'll get a complex spectra. Mismatched cells. If the cells holding the analyte, the UV visible region cells are also known as the cuvettes. So if the cells holding the analyte and blank solutions are not of equal path length, and equivalent in optical characteristic, and intercept will occur in the calibration curve. And depending upon our law, Beer-Lambert law, we can calculate the absorption or the concentration keeping the path length constant. References are given in this slide. You can refer to these. Thank you. For any queries or any suggestions, you may comment in the comment box.